Good day. So, today we will be talking about multiplexing. Multiplexing is about sharing a medium. That means different users are sharing the same medium for communication at the same time. Okay. Now, under the simplest condition, a medium can carry one signal at any moment, because if there are two signals over there, they are going to interfere and the signal will get garbled. But for multiple signals can share one medium, the medium must somehow be divided, giving each signal a portion of the total bandwidth. If you remember that a particular frequency range around one particular frequency is called a bandwidth, and this bandwidth is the most valuable resource so far as communication is concerned. So, what we try to do is that we try to use this bandwidth somehow to facilitate the communication between a number of pairs of senders and receivers. So, that is the idea of multiplexing. So, there are various reasons why we want to use multiplexing, and the chief one is that transmission service is very expensive. Leased line, packet switch network, for example, laying of lines is in itself a fairly expensive and complex proposition, and once you lay a line, you really like to utilize it to the maximum. The other thing is that if you can use that for the maximum amount of communication, multiplexing and compression techniques are the techniques which we use for this purpose, and that saves a lot of money for the business. And when you can send a lot of data through the same line, the data capacity of the line increases. It becomes more cost effective for the company, and most data devices individually they require modest amount of data, but when a number of users their requirement are aggregated together, the sum total may be quite a substantial bandwidth. The current technique to accomplish this includes frequency division multiplexing, wavelength division multiplexing, time division multiplexing, and code division multiplexing. We will look at many of some of these at least. So, let us see. So, this is the scheme of multiplexing. You have one multiplexer, and then you have n inputs on one side. So, these n inputs are coming to the same multiplexer, they are getting mixed up in some fashion and they are being sent over the same physical link. And on the other side, depending on in which fashion you have put them together, they are sort of separated into different lines. So, these different lines on the right, they can now go to different recipients. So, just as on the left we have different senders and we have different receivers over here. So, so a number of sender receiver pairs is utilizing the same physical link in between. The alternative to multiplexing of course would be direct point to point connection. This has a number of problems. First problem is of course that you need those lines that we were talking about. You need line for each device, you need a large amount of wiring if they are on different floors. And another important point is that you need a lot of I/O ports on the computer side, which really is not feasible. Okay, you may have a few I/O ports, but you cannot have hundreds of I/O ports there. I mean, at least it is very difficult to have hundreds of I/O ports there. So, that is also another bottleneck that we wish to address. Another approach could be, so this is a somewhat older approach, which is that of a multi-drop line. So, host polls machines to see who wants to send and then uses the same line, saves I/O ports. Total communication load is not greater than the data rate of the line. So, these are actually the simple approaches. So, using a multiplexer approach, so all the devices their data is multiplexed on one side, sent through one line, and the number of lines in equal to the number of lines out. Link carries multiple channels of information. Now, for the types of multiplexers, as I mentioned, that we have FDM, that is the frequency division multiplexing, TDM, that is the time division multiplexing, STDM, that is the statistical time division multiplexing. So, we will look at these. Just quickly before we get into the details of each of these, in time division multiplexing, each user periodically gets the entire bandwidth. That means, the entire channel is dedicated to one user, but only for a short period of time, for a small burst of time. After that, it is somebody else's turn. So, we will look at the details of this later. And the other common approach is the frequency division multiplexing. So, here the frequency spectrum is divided among the logical channels. So, here we have only one physical channel, but we want to have a number of logical channels. So, the frequency spectrum of the channel is divided. Each user has exclusive access to his channel. Okay. This FDM sends signals in several distinct frequency ranges. One of the oldest use of frequency division multiplexing is in radio. For example, we have this electromagnetic field, this our atmosphere, let us say, through which electromagnetic radiation can pass, and of course, electromagnetic radiation can be of various very large range of bandwidth. The whole range of bandwidth is there. Out of that, the so called radio frequencies constitute just one part of it, a fairly important part of it, and this whole bandwidth of radio frequencies, that is divided into small channels, and each channel is given to one particular station. And on the receiver side, on the radio side, what we do is that we tune our radio, let us say, to one particular frequency, so that it receives signal from that particular station only, although a number of stations are all transmitting at the same time. So, this is an example of multiplexing. Another example of multiplexing, the same frequency division multiplexing, we see nowadays in the cable TV. The cable TV providers gives one cable to the one coaxial cable to the premise, which is connected to the TV. So, that one coaxial cable apparently is carrying number of channels, maybe hundreds of channels these days. So, what is done once again is that all the frequencies which can travel down this cable, that is broken down into a number of logical channels, and each channel is dedicated to one particular station. So, that is how we carry multiple video channels on a single cable. Of course, point to point nowadays is out of question. Imagine cost of stringing wire for each channel. So, you will have 100 cables coming into your building, which is not really possible. Now, each signal is modulated onto a different carrier frequency, and carrier frequencies are separated by guard bands. Okay. This guard bands is important because you know that one particular channel, it may be a radio channel or it may be a TV channel, the principle is the same everywhere. So, that uses some around some middle frequency, maybe some range of frequencies. Now, the next station, maybe a TV station or radio station, whatever it is, that can occupy, that has to, first of all, that has to be non-overlapping. The range of frequencies which is assigned to the second station has to be non-overlapping with the range of frequencies which are given to the first station, and not only that, between these two there must be some separation in frequencies. Otherwise, what will happen is these two signals are going to interfere with each other. So, that is a guard band. Bandwidth of the transmission medium exceeds required bandwidth of all the signals because of these guard bands which have to come in between. Usually, for frequency division multiplexing, analog signaling is used to transmit signals. Okay. Broadcast radio, television, cable television, AMS cellular phone system use frequency division multiplexing. AMS is an old cellular phone system that was there in USA, Nowadays of course, the kind of cellular technology that we have in our country that uses more complex multiplexing techniques, maybe I will mention it later on. So, these systems all use frequency division multiplexing. This technique is the oldest of multiplexing techniques. So, assignment of non-overlapping frequency ranges to each user or signal on a medium, thus all signals are transmitted at the same time, each using different frequencies. A multiplexer accepts inputs and assigns frequencies to each device. So, just and the multiplexer is attached to a high speed communication line, because all these frequency bands for an individual users is going to add up to a fat range of frequencies. So, the communication line must be able to handle this whole frequency range, or in other words the communication line has to be high speed. A corresponding multiplexer or demultiplexer is on the end of the high speed line and separates the multiplex signal, because on the other end you have to separate them out. Since it involves analog signaling, it is more susceptible to noise. This we have seen that analog signals are more susceptible to noise, whereas in digital signals we can sort of clean the noise more easily. So, this is a diagram, if you note that for a particular user, suppose user 1, if we give the channel 1, now along the time this channel 1 is entirely dedicated to user 1 for all time. Okay. Similarly, channel 2, which is at a different frequency. So, the frequency is on this side and time is on this side. So, the another channel, this channel 2, which is on a different frequency range, once again user 2 gets to use this frequency for the whole time. So, this is the simplest kind of scheme for so that this whole frequency band, frequency is being divided. So, that is why it is called frequency division multiplexing. So, as was mentioned, the frequency channel is divided into logical channels. Each user hangs on to a particular frequency. The radio spectrum and a radio are examples of the media and the mechanism of extending information from the medium. So, this is here is another picture of the same thing, say channel 1 and then so the channel 2, channel 3, they are all sending some signals. So, if you plot them across the frequency versus the signal strength maybe, so you get a picture like this. So, this is the first channel, this is the second channel, this is the third channel. In between this part here is the so called guard band. So, this frequency is not used by either of them. Okay. There is some overlapping because due to noise and other issues. So, we will not get into that. So, due to that over here, but as such, so this is what it looks like, the frequencies bands are all separated. Okay. So, here is another diagram which shows, let us say you have the host and a 300 bps line, a number of 300 bits per second line are being multiplexed to 1200 bps line. So, and then there are some guard bands. So, maybe 300 to 1013 hertz is one, and then 1493 to 2206 hertz is another line, maybe 2686 to 3400 hertz is another line. So, these are the 300 bits per second sub channels, okay, and there you have the guard bands in between, and on the other side again you have this multiplexer demultiplexer which takes it to different users. One problem with FDM is that it cannot utilize the full capacity of the cable. It is important that the frequency bands do not overlap. So, that is why you have to give the guard bands. So, the full capacity of the cable is not utilized. And the other disadvantage, of course, we will summarize these advantages and disadvantages later on. The other disadvantage is that it is sort of a bit more prone to noise because we are dealing with analog signals here. FDM is usually used to carry analog signals, although modulated digital signals can also be sent using this technique. We have another type of signals which is called wavelength, another type of multiplexing techniques called wavelength division multiplexing. Wavelength division multiplexing is the same as the frequency division multiplexing, only thing is that here the operating frequencies are much higher, actually they are in the optical range. So, that is why so somehow it is given a different name like wavelength division multiplexing. You know, different wavelengths means different frequencies. So, if you are doing wavelength division, it is the same thing as doing frequency division, and this is used in optical fibers. Okay. So, this is the same as FDM, but applied to fibers. There is a great potential for fibers since the bandwidth is very huge. Okay. As I mentioned, the operating frequencies are very high. So, even a slight percentage deviation from the mean operating frequency gives you a very large bandwidth. So, you can sort of compact a lot of channels in a at that high frequencies. So, fiber have a large bandwidth capacity, and with different energy bands are passed through a diffraction grating prism, combined on the long distance link and then split at the destination. So, this has got high reliability as well as very high capacity, two very interesting properties. So, multiplexing and demultiplexing for wavelength division multiplexing is of course very simple. If you take a prism, so what it will, you know that a prism, if you send white light through it, it breaks up into all the different colors, because the refractive index of the prism that varies with the frequency. So, different frequencies can come in, and you can make it to the same light source, or so to say, in this, and on the other side you can use a prism to break it up. Of course, I have shown a prism here for simplicity, usually maybe something like a diffraction grating is used. So, if you look at the fiber spectrum, you have maybe if you just plot the power versus the frequency. So, one fiber may be giving at this frequency, another fiber may be delivering power at this frequency. So, if you put them together simply, then you get, this is the power versus frequency or power versus lambda kind of plot that you get. So, wavelength division multiplexing multiplexes multiple data streams onto a single fiber optic line. Different wavelength lasers called lambdas, lambda, you know, traditionally lambda is used for denoting a wavelength. So, somehow, so lambda is quite extensively used in this optical communication domain. So, different frequencies are called, they are called different lambdas. So, they are called lambdas. So, they transmit the multiple signals. Each signal carried on the fiber can be transmitted at a different rate from the other signals. You see, so this is one very interesting thing of fiber, that the different colors, although they may get mixed, but finally again they will be separated. So, what rate of data, what protocol, etc., that they are carrying. So, your fiber system is really, I mean, it is transparent to all that. So, so that is a good thing, different systems can be pushed through the same fiber, and of course, as I mentioned that fiber has a very high capacity. So, you get to push in a lot of channels into the same fiber. Dense wavelength division multiplexing, also called DWDM, they may combine as many as maybe 30, 40, 50, 60 or more channels these days into one fiber. Okay, and each of these channels have a very high capacity. So, a DWDM channel has a very high capacity, and it is improving all the time. People are finding I mean ways of packing more lambdas into the same fiber, and it is supposed to be quite scalable into the future. But of course, if you want to pack those wavelengths in a very dense fashion, your equipment becomes somewhat costly. A cheaper alternative which has come up recently is called CWDM. So, dense wavelength division multiplexing is called DWDM. A cheaper version is called coarse wavelength division multiplexing, or CWDM. So, in the CWDM, the channels are more widely spaced. on the spectrum. So, the channels are more widely spaced. So, your multiplexer, demultiplexer, all these costs go down and it becomes a cheaper alternative, but still you can push in a number of wavelengths into the same fiber. Okay. Now, we come to the other very important multiplexing technique called time division multiplexing. Okay. As a matter of fact, this is extensively used specifically in our computer communication or telecommunication. Time division multiplexing is very extensively used, especially on the service provider side. So, we will look at these later on. So, sharing of the signal is accomplished in time division multiplexing by dividing the available transmission time on a medium amongst users. So, time is being divided. What is done is that, as I mentioned before, that each user get a small burst of time in which at that time the entire channel and the entire bandwidth is at his disposal. But as soon as that short duration of time is over, then it is somebody else's turn to send, and then it is somebody else's turn to send, and this way maybe in a round robin fashion after some time it will come back to the original user, so that he can send his next burst of data or voice or whatever it is. Usually we use digital signaling in time division multiplexing almost always. So, digital signaling is used almost exclusively. Now, time division multiplexing comes in two basic forms. One is synchronous time division multiplexing, the other is statistical or asynchronous time division multiplexing. So, we will look at synchronous time division multiplexing first, because that is the simpler scheme, and then we will look at statistical multiplexing. So, the same multiplexing scheme looks like this. So, this is the frequency, the same plot. If you remember in the previous diagram, when we are doing TDM, we were slicing this channel in this fashion. Now, we are slicing it in this fashion, that means time is divided. So, channel 1, channel 2, channel 3, channel 4, channel 5, channel 6. So, they get the entire frequency range for a small burst of time, and when suppose only 6 channels are being multiplexed. So, after 6 again it will becomes the turn of channel 1. So, at this time, so channel 1 sends the first burst of data etc. using the entire frequency band during this time period, and then during this time period. During this time channel 1 is not sending anything. So, it is quiescent. So, time is getting divided in this fashion. So, this is why this is called a time division multiplexing. So, this is the schematic of a time division multiplexing system. Like FDM, time division multiplexing saves money by allowing more than one telephone call to use a cable at the same time. So, you have this say term in terminal number 1, terminal number 2, terminal number 3. So, terminal number 1 is giving at this particular time, then terminal number 2, then this terminal number 3, and over here on the other side this sequence and the way it goes, that is known, that has to be known. So, whatever signal comes at one particular slot at this slot, maybe this multiplexer knows that this is must be for receiver number 1, and this is next slot is for receiver number 2, next slot is for receiver number 3. So, on the receiver side, so it just knows that if it is this time slot, it is for some particular user. Of course, this is a synchronous time division multiplexing, because this clock and this clock has to be synchronized, otherwise there will be problem. Now, instead of dividing the cable into frequency band, TDM splits cable usage into time slots. Each channel is given a regular time slot in which to send a PCM signal. This is another view of the same time division multiplexing. Actually, in actual practice, we will go into the details of this later on. Actually, this time division multiplexing can be done in a hierarchy of manner. So, we will look at this hierarchy later on. If you remember from our digital signals discussion, that our voice, because it is say up to let us say 4 kilohertz is our voice signal. So, you because of Nyquist theorem we require 8 kilo samples, that means double that rate, that means 8000 samples per second for capturing voice, and for each sample, now that has to be converted, each sample is an analog value. So, that the value that has to be converted to a digital signal, maybe 8-bit digital signal, that is called the PCM, which is a pulse coded modulation, that 8-bit code, that means there are 256 different levels that this is distinguishing, which is very fine. Our amplitude of voice, if you divide it into 256 parts, so you are making very fine distinction. So, that gives you 8 bits per sample, 8000 samples per second. So, that comes to 64,000 bits per second. Okay. So, this is a very basic rate, and this rate has got a name. So, we will go into these names and all later on. So, a number of such channels may be multiplexed together. So, since we require 60, so since this is a very basic rate, so 64,000 bits per second, and if you so every so each channel, now a number of such channels may be grouped together to form one particular higher level channel. Okay. And different higher level channels may again join together to make a hierarchy of channels. So, this is what is shown over here, these T1 etc. So, do not bother about these figures at the moment, because we will look at these later on. So, T1 is one particular rate at which some of these signals come. So, there are standards, worldwide standards, actually there are 2 standards. So, we will talk about it later on. So, standards of the rate at which these signals come. So, they get they sort of join together and form a stream of T2 stream, and different T2 streams may, these different rates have different names like T1, T2, T3 etc. will form a T3 kind of frame. And as you can see that the bandwidth is increasing all the time. Okay. So, this is as a T1 rate is 1.544 megabits per second. So, in time division multiplexing used for digital signals or analog signals carrying digital data, data rate of transmission media exceeds data rate of signals. So, this has to be there, otherwise your TDM system will not work, because in that small burst of time which is given to a particular user, in that burst of time that user should be able to send whatever digital data it had accumulated during the time during that time as well as the previous epoch during which it was quiescent. And because it was quiescent, because at that time it was other people's turn. So, it had sort of, it had maybe a buffer kind of thing where all these bits were getting accumulated, and when it gets a small burst of time, during that burst of time it sends all the bits in that buffer to make it empty, and then it becomes quiet again. So, it will accumulate the bits again in the buffer, and then again when it gets the next burst of time it will send all the bits. So, data rate of transmission media has to exceed the data rate of signals. It uses a frame. Okay. A frame means a number of bits and bytes put together to form one particular unit at which to send it over. Now, one slot for each slice of time. Okay. Now, what would happen is that during this slot you may send now a slow device during his slot will send lower number of bits. A very high speed device will send a large number of bits, but your slot will come periodically. Okay. One or more slots for each device is equal to channel, and time slots are transmitted whether source has data or not. Now, this is one particular problem with time division multiplexing. Think about this, that on the receiving side, receiver side is blind, it does not know this stream of bits which is come is for whom. So, the only way he knows that this is the time slot for receiver number I. So, he will simply send those bits to receiver number I, okay, and so on in a round robin fashion. Now, what happens, suppose the senders are also S1, S2 to Sn, receivers are also S1, S2 to Sn. So, we have this, so Si is sending to Ri. Now, what happens if Si has nothing to send at that particular point of time, Si has nothing to send. Okay. Now, during that time it is not possible for the multiplexer to or the demultiplexer in the normal scheme of things and the way the kind of scheme that we are talking about here, that it is not possible for him to send somebody else maybe Sj's signal during that time, although physically it would be possible. Okay. But then on the demultiplexing side it would cause a problem, because the demultiplexer now would not know whether this bit is for I or for j, Ri or for Rj. So, that is why even if Si has nothing to send, that slot will have to run empty, you cannot utilize it any further. Okay. So, this is the weakness of time division multiplexing. So, which we try to sort of address in a different scheme we will be talking about just now. So, the synchronous time division multiplexing, remember that this is synchronous because the multiplexer and demultiplexer has to agree about the slot of time. The original time division multiplexing, the multiplexer accepts input from attached devices in a round robin fashion and transmit. T1 and ISDN telephone lines are common examples of synchronous time division multiplexing. Now, if one device generates data at a faster rate than other devices, then the multiplexer must either sample the incoming data stream from that device more often than it samples the other devices, or buffer the faster incoming stream. If a device has nothing to transmit, the multiplexer still must insert a piece of data from that device into the multiplex stream. It may be a dummy data. Now, before I talk about the other kind of TDM, which is that statistical time division multiplexing, I must mention that there are hybrid multiplexing schemes also. That means, in the hybrid scheme what you do is that you take a frequency band, alright, and in this band, so it is that way, it is like frequency division multiplexing. So, you break up your entire available channel into a number of bands, but each of the band, instead of in the pure FDM we were giving it to only one user, but this band is now allotted to maybe a number of users who uses TDM on this band. So, this is a combination of FDM and TDM. So, there are such kind of hybrid multiplexing systems are quite widely used these days, and one good example are many of the cell phone communication that goes on that uses hybrid that may use hybrid kind of multiplexing systems. So, in hybrid multiplexing system both FDM and TDM may be combined. The available channel is broken up into frequency bands. In each band multiple channels are accommodated through TDM. Okay. Now, we talk about the other kind of time division multiplexing, namely statistical multiplexing. This is time division, but on demand rather than fixed. So, we reschedule link on a per packet basis, and packets from different sources are interleaved on the link. Remember, as I mentioned that the disadvantage of time division multiplexing is that even if the sender does not have to send anything, but that time slot now will go empty, we cannot utilize it, because otherwise on the demultiplexer side we will not be able to decipher who is it in the pure time division multiplexing. This is sought to be addressed in statistical time division multiplexing or STDM. What is done is that the packets are sent on demand. That means, if somebody has to send and the channel is free, it will be sent. Okay. It is as simple as that. Of course, if everybody has to send, then you have to once again have to do some kind of scheduling and do in a round robin fashion in a simple vanilla case, or you can do more fancy kind of scheduling. I am not going into that. So, this utilizes the channel in a much more efficient manner. But you have a problem, and we know what the problem is. The problem is on the demultiplexer side. On the demultiplexer side, now one particular time slot being allotted to one particular sender or receiver, that relationship is no longer there. And if that relationship is no longer there, how do you make out on the other side whether this is meant for whom? So, you have to have that address inside that data stream. That means, inside that data stream there must be something which tells the receiver at the receiver end, the demultiplexer, that this is meant for that receiver. Okay. So, you have to have the address, at least the destination address in the packet, so to say. Okay. So, now I am calling it a packet, the whatever the burst of data that is sent in one particular time slot. So, it allows connection of more nodes to the circuit than the capacity of the circuit. Okay. That is because, I mean, how this is possible? This is because usually our communication is always bursty. For example, when I am talking, I may require 4 kilohertz when I am making a sound, okay. But then there are periods when I am quiescent, that means I am not talking at all. So, so overall if I can utilize that, so maybe my effective rate of utilization of that channel will become more than 4 kilohertz, because so one user is being is using 4 kilohertz. So, this way, so each of the channel, the same thing happens and much more dramatically in the world of sending and receiving data. Data traffic is inherently very bursty, which means that one computer is communicating with another computer. So, this will do so in bursts. So, it will want to send a lot of stuff, suddenly it has something to send. So, you want to send them fast in a burst, and then for a long time it will be quiet, there will be nothing, because it will go there, maybe get processed over there, maybe some user sees it, sees that data and things like that. So, it is a quiet for a long time, then again it sends another burst. So, it is very bursty. So, in between these bursts there is a lot of time. So, while that burst is there, maybe I am using it at a very high speed, but then other people can share it. So, that is why in some sense it allows connection of more nodes to the circuit than the capacity of the circuit. Works on the premise that not all nodes will transmit at full capacity at all times. Must transmit a terminal identification, as I said, the destination identification has to be there, and may require storage, because you may two different sources may want to send at the same time, and both of them may land up there hoping that the channel will be free. So, I am calling it a multiplexer at this point. So, at the multiplexer end you will have to store them and then forward them over the channel as and when the channel becomes available. So, this is a picture of once again getting multiplexed. So, they are getting multiplexed as they come. You see that this is the queue in between. So, you have this buffer over here, this is the memory where the incoming packets are getting stored, and they are making a queue. Okay. So, there are a number of packets here, and from this queue one by one as they come. So, it is not necessary that they have to go in a strict round robin fashion. As they arrive, they are being pumped into this transmission channel. On this side, on the demultiplexing side, it will look at the some receiver address which is also contained in within this packet or cell, whatever it is, and then sent to the proper receiver. So, we buffer packets that are contending for the link. Packets queue may be processed first in first out, but as I said that this is the most vanilla kind of scheme. There are other fancy schemes. For example, you may have a high priority queue. So, some of the users who may be paying more, you may have a high priority queue for them. So, from that queue is processed first before the other queue, and all kinds of possibilities are there. But of course, since you have a buffer, it is theoretically possible, and since your capacity of the link is it cannot handle if all the senders decide to send at the same time, which may happen. in which case it will start filling it in the buffer, but the buffer may also overflow, which means that there is some congestion in the network and then some data loss is there. So, to summarize, a statistical multiplexer transmits only the data from active workstations. If a workstation is not active, no space is wasted on the multiplex stream. A statistical multiplexer accepts the incoming data streams and creates a frame containing only the data to be transmitted, and also as I said that this frame will also contain the some kind of destination address. So, this is an example to identify each piece of data in address is included. So, data of C as well as the address of C, data of A as well as the address of A. So, the address also has to go with the data. This of course is under the assumption that all these data packets and this address also together all this packet length is fixed, which is the case in some systems like ATM etc. This size is fixed, but the size may vary also, and if the size varies then you will have to include the length of A also. That means, this is the data of A, what is the total length of A, or maybe the data part if this part is fixed depending on the scheme, and then the address to which this is destined. So, please so all these things are put in the form of a frame and then it is sent. Finally, I would like to summarize the advantages and disadvantages of each of the schemes. By the way, in the beginning I mentioned something called a code division multiplexing also, which is also a very interesting scheme. So, we will talk about code division multiplexing when we talk about multiple access. Okay. So, there are actually there are two terms, one is multiplexing, the other is multiple access. Usually this is how we usually mean it, but that distinction is getting blurred these days, but usually when you are multiplexing, usually the sources are sort of converge to the multiplexer in some sense, alright. So, the sources are converged to the multiplexer in some sense, and it goes to the demultiplexer where it diverges. So, there is a specific convergence which is there. That means, a number of, let us say telephone lines are getting multiplexed. So, a number of telephone lines will come to the let us say the local telephone exchange. So, at there all these maybe they are all destined for some other exchange. So, all these lines will be multiplexed together. So, they are happening physically in one place. Now, if the problem is this, that once again you have a shared medium, but the media but the users are distributed. Okay. In that case, we call it a multiple access system. Okay. So, CDMA is a multiple access system, as well as you can in some sense you can call it a multiplexing system also. By the way, as I said that this distinction is slowly getting blurred these days. For example, you are doing some kind of multiplexing, I said when you come to say cell phones. Okay. So, we are doing some, let us say hybrid kind of multiplexing, that means we have got a combination of FDM and TDM, that means we have some bands of frequencies which are being used by a number of users, but these users are not at the same place. Okay. So, they are carrying some wireless station, that means they are carrying their mobile handsets and they are at various locations, even for the same base station, under the same base station, they are at various locations in that area, so to say. So, that is what I said, that the distinction between multiplexing and multiple access is getting a little blurred these days, but anyway we will discuss code division multiplexing or multiple access when we talk about other kinds of multiple access. As you can guess that there are time division multiple access, then there are frequency division multiple access, and of course, this code division multiple access is also there. So, we will discuss it there. Coming back to the schemes that we did discuss, namely FDM, I mean one thing good about, I mean what are the advantages or good things about each of these schemes. FDM is of course simple, and being simple means that also means that this is cheap, and then this is very popular, and as I mentioned that this is the oldest multiplexing technique. So, all your radio uses this and a lot of other systems use this. TDM is specifically for digital signals. Okay. So, for digital signals TDM is very nice, and then you can have a multiplexing hierarchy, that is another advantage of TDM. Why is it an advantage? Well, the advantage is because of this, that at different places we may require different levels of bandwidth and speed. Just think about this. Suppose we have this telephone network. Okay. Now, you may have, let us say you have a small exchange. So, the small exchange naturally will have a small number of users, and only a few of those users will want to communicate or make an STD call, let us say, or also communicate with some other telephone which is under some other exchange. So, the few will have to be multiplexed together over at that small exchange, and then it will be sent to the trunk exchange. Now, from there it may go to another trunk exchange and so on, and finally it will reach. Now, at the trunk exchange what is happening is that once again various such connections from the different local exchanges are coming and converging to the same trunk exchange. Now, when this trunk exchange is communicating with a trunk with another big trunk exchange, so what is happening is that there are a lot of tributaries flowing into it. So, there is a lot of channels. So, basically the same signal, mind you. So, we are doing time division multiplexing, that means the rate at which the receiver at this end is sending, that same rate has to be maintained throughout, but then instead of flowing in small tributaries, now it has moved into a very fat channel. Okay. So, we require a multiplexing hierarchy. So, such multiplexing hierarchy are easy to implement using time division multiplexing. We will see more of this when we talk about synchronous digital hierarchy later on. Now, STDM, its advantage. So, we are only talking about advantages, we will talk about disadvantages, we will just remind you of the disadvantages later on. In statistical time division multiplexing, this is certainly more efficient bandwidth use. Okay. This is much more efficient because as I mentioned that data, especially data usage and usage in general may be very bursty, and if it is bursty, then during the quiescent period ordinary TDM is just wasting the channel, whereas STDM is making full use of it. So, it is more efficient bandwidth use. So, that is a good thing about STDM. Another advantage of STDM is that frame can contain control information. Okay. Since you are putting you have put a frame, you can sort of, as I said, that maybe with the address of the receiver or the or maybe other kinds of control information can be put in the frame, and then the packets can be of varying sizes. So, these are advantages of STDM. Not all STDM systems will allow these varying sizes. For example, ATM will not allow varying size cells. In ATM the packets are called cells. So, they will have a fixed size, but some systems may allow. Okay. So, that is a good thing about STDM. WDM, we are writing it separately because although as I said that this is some form of FDM, but this has a this is works with a very high capacity. So, very high capacity, it is scalable, and this has got low noise sensitivity. That is another good thing about the communication in the optical domain. In the optical domain, suppose it's you are doing it in the electrical domain through a wire maybe. So, if there is some kind of electrical noise somewhere, some motor has started, or very bad is if there is some lightning somewhere nearby. So, a lot of noise will get into that, this your electrical wire will catch all this noise, whereas an optical fiber is not going to catch any of this noise. So, it is very immune to noise. So, that way it has got a very low noise sensitivity, which is very good, and very high capacity, and you can scale it to still higher capacity using DWDM and so on. Now, just a quick look at the disadvantages. FDM, as I mentioned in the earlier, this is susceptible to noise, wasted bandwidth because of this guard bands, etc. And of course, one frequency, whatever the small band is being permanently given to one user. So, and his behavior is very bursty. If it is, then that is a lot of wasted bandwidth there also, and then we have a limited frequency range. In TDM also wasted bandwidth for the same reason. STDM takes care of that problem in TDM, but this is very expensive. Okay. Traditionally, we did not have any other alternative, so we used STDM a lot when high speed was necessary, especially in the service provider side. So, we used STDM, and WDM is somewhat more costly than TDM and FDM, but since this is a developing technology, this cost is coming down, and that means the WDM cost is coming down. So, but it is still somewhat more costly than TDM and FDM, but maybe less costly than STDM. So, we have looked at the different multiplexing techniques today. In the next lecture, we will look at one kind of network which is very widely used for data and all kinds of communication, namely the telecom network, the telecommunication network, because please remember that although it is called telecommunication network and it was traditionally for people talking over telephones for voice, etc., but that is the network which carries most of the wide area data traffic today. So, that is a very important one. So, we will talk about it in the next lecture. Good day. Today we will talk about telecom networks. Telecom networks, that means the kind of the network that is used by telephones, and of course, nowadays by a host of other things, as we will discuss. This telecom network is very important in the sense that first of all it is one of the earliest networks that we had, that is one thing, that is quite old, and secondly the telecom network even today is mostly used for a wide area communication. Okay. We have, I mean, comparatively we have much fewer entirely or exclusive data networks. So, we will look at the evolution of telecom networks. Well, when Alexander Graham Bell developed the first telephone, it was a couple of telephone instruments connected by a wire. Now, if you are trying to connect more than one people, that means more than one subscribers are there. So, taking this principle forward, you will have to connect everybody to everybody else through a wire, which of course becomes very unwieldy very soon, okay, because connecting or stringing a wire between every pair of telephones that might want to communicate was not a good long term strategy at all. As you can see that very soon we have a veritable jungle of wires, and of course it is, it is costly and it is very difficult to manage. Even at the subscriber end, you cannot handle so many wires coming into your premise. So, a better idea was to connect all the telephones to a central switching office. There an operator could connect one telephone to another via a switchboard. Okay, that is the next figure that you see, that the number of wires have come down. As a matter of fact, in the figure at the top, if you have n subscribers, so naturally you have n into n minus 1 by 2 links, which is approximately n square kind of links, whereas in the latter case you have only n links. So, the number of links as n becomes large, and you know today there are so many telephone subscribers. So, there is no question of connecting them individually, you have to connect them to a central switching office. So, so this is the by the way, even then, once again I mentioned this earlier in the lecture, you must remember that it is not that we have a whole parallel network for data from computers etc. all over the globe. Okay, it is not there, because the telecom network has been around for a long time. It had a long and very excellent history. So, that is why even today most of the wide area network traffic is still rides on this telecom network. Okay. So, we have a lot of, so originally it might have been a packet, then it might be sort of made into some kind of a session for which there is some part of the connection is dedicated. So, all kinds of technology has come in, but even today most of the wide area networks are based on the telecom networks, and telecom. So, that is one side of the story. The other side of the story is that telecom networks, the telecom people are actually in the process of routing some of the voice calls and maybe some of the other kinds of calls into this packet kind of technology. So, the DSL at subscriber end, voice traffic is transmitted as standard analog telephony signal. Data traffic is transmitted over the same line but via DSL modem that transmit data as high frequency digital broadband signals on the same line. Okay. So, if you have DSL modem, you can have both your voice as well as data at the same time, unlike very ordinary analog lines. So, DSL at the central office end, CON, the signal passes through a splitter as I had shown and a local loop management system. So, the subscriber line access multiplexer is there. So, this figure we have already seen. So, you can just have this figure. So, you have this DSLAM and the loop management over there. So, the broadband digital signals are directed to a DSLAM that terminates and coordinates traffic from multiple local loop lines. From the DSLAM, the traffic is sent to a router and then to the internet. Okay. And finally, we have the loop management system, which may be in front of the splitter or behind the splitter. So, this comes to various functions are there like giving the connections and testing, and all these service kind of these things are done through the local loop management. Thank you.